Chapter 2, Periodicity and the Electronic Structure of Atoms. This chapter deals with electromagnetic radiation. All light waves consist of electromagnetic waves, which means that there is an electric field component that is always running perpendicular to the magnetic field component, and they travel at the same rate. So the speed of light measured in a vacuum is 3.00 times 10 to the 8th meters per second, which means that no matter what the wavelength is and what the frequency is, these two things multiplied together will always have to equal the speed of light. So knowing this, we can always determine the wavelength or the frequency if we know one. So here's a scale representing the different types of electromagnetic radiation, going from highest energy to lowest energy. So gamma rays, X-rays, UV rays, all very high energy, which means that they have a large frequency and a very tiny, short wavelength. Here we have the visible region of light from 400 nanometers to 700 nanometers. And then we get into less and less energetic radiation. So infrared, which is heat, microwaves, and radio waves. If we look at a radio wave, it is very low energy, has a much smaller frequency, and is much, much larger in its wavelength. So what do these terms exactly mean? So for our waves, we have a wavelength and a frequency. And the wavelength is defined as the distance between either two peaks, or we can measure it as the distance between two of the troughs in a given wave. A frequency is how many times does a wave pass through the node here in a given amount of time. And we normally measure that in terms of how many times does the wave go up and down in 1 second. The amplitude of the wave is simply the height, and the speed is how fast it's traveling. And all electromagnetic radiation has to travel at the same speed, which is the speed of light. So wavelength measures distance. Frequency is actually a measurement of inverse time. We measure this in hertz, or inverse seconds, which is seconds to the -1. So into some experiments dealing with waves, light waves. When light passes through two closely spaced slits, what we see is an interference pattern. So here we have a beam of light. If it travels through one slit, it would go straight, and we would see a focused dot of light here on this screen. However, if the light can pass through two different slits, what we see is this pattern here that develops. And this pattern is resulting from the constructive interference, so where the waves are overlapping, they're in sync with each other, or they're considered to be in phase, which is where we see these bands of light. Versus when there's destructive interference, which means that the wavelengths are basically canceling each other out because they are out of phase. So we see this pattern, and if light didn't travel in waves, we would not see this pattern. We would just expect light to travel through and hit the spot here, light to travel through and hit the spot here. So this proves what we think about light in terms of that it does travel as a wave. Another experiment, Planck's quantum theory. A heated solids problem. So what happens when we heat a solid? Well, if you use your stove, you'll notice that your burners will glow red when they are heated. If we look at fires, we see different colors, excuse me, in a fire. We know things can be white hot or blue. Just depends on what the temperature is. So Planck discovered that there is indeed a direct relationship between temperature and the color that we see, which means that there's a specific wavelength of light. So temperature depends on its wavelength. Because of this, we don't see a wide spectrum of colors. It either glows red because it's at that temperature, or it glows white because it's at that temperature, or it glows blue because it's at that temperature, which he then determined to say that energy is emitted or absorbed in discrete units, so quantum. So this notion of quantum, meaning a little packet, tiny, tiny amount of light. And what he discovered is no matter what, the energy was always some integer, some multiple of h times v, where h is Planck's constant, 6.63 times 10 to the negative 34th joules seconds. Notice joules and seconds are multiplied by each other. So energy is directly proportional to the frequency. And we're not talking about huge amounts of energy, but this energy is stepwise, which is an important factor. Einstein continued on with what Planck did and studying the photoelectric effect. So they've been doing this. They shine a certain type of light on a metal, and then they can catch the electrons, because electrons are negative, and they'd be attracted to this positive metal here, and goes through, and then the voltage is measured. So how many electrons are captured, we can see what the voltage is. Now, depending upon the wavelength of this light, or the energy, right, the energy of this light, something would happen or nothing would happen. If we didn't have the wavelength of light that was necessary, no matter how bright the light was, no electrons would be ejected. Now, if you have what was called the minimum threshold, this minimum energy, which we can indeed bounce electrons off of here, we would see that happen. If you use a much more energetic source of light, we not only would see the electrons ejected, but they would have a certain amount of kinetic energy associated with them. And the brighter the light, if we were at that minimum threshold, the more electrons that we could get. So you could have a really, really brightly shining light, but if that specific wavelength of light was not energetic enough to eject these electrons, nothing would happen, no matter how bright the light is. So there's a minimum energy that is required to eject an electron from a metal surface. Because of this, Einstein determined that light is both wave and particle in nature. So what we call particles of light are simply photons. And this here gives us energy of light equals the kinetic energy plus this work function. And the work function is specific for each type of metal. And that relates to that minimum amount of energy, or that threshold with which the light has to be, that wavelength, that minimum wavelength. Bohr continued on and studied the hydrogen atom. And what he discovered was that here we have a hydrogen discharge tube connected to a high voltage source. So we're shooting electrons through here. Now, we can focus this beam of light through a slit and then diffract it through a prism. And what he saw was that there was a specific line spectrum for hydrogen. There were always these same specific colors at these same specific wavelengths, no matter how much of a sample of hydrogen you have. So this is what we call the line emission spectrum of hydrogen. You will always see these colors for hydrogen. It's like a fingerprint. Every element has a different line spectra. So here we have some of our group 1 metals, our group 2 metals, some transition metals, non-metals. Specifically, we have some noble gases. Neon is familiar, right? We see the bright neon lights. Sodium, there used to be sodium lamps and they would glow yellow. Potassium, if you burn it, you can see a really, really kind of bright pink color. So we have all of these different line spectra. And like I say, they are unique to the element from which they are produced. So you can use line spectra to identify elements. And they used to do this quite a bit back in the day. So continuing on with his hydrogen atom, Bohr said that electrons can only have specific values. So this goes back to quantized, which is what Planck said. We can only have discrete units, only have discrete stair steps, basically, of what energy is allowed for an electron to be at. So for example, the smallest, the closest to the nucleus that we can get would be n equals 1, this distance. Then we have n equals 2, which is farther away, n equals 3, which is much farther away. And an electron can transition between an outer shell and an inner shell. And when it does this, it gives off a photon of light. So high energy electron can drop down to become more stable because the energy level, as it increases as you move farther and farther away. So we have this equation here where energy is related to the principal quantum number, that distance from the nucleus, and then we have the Rydberg constant, which allows us to convert into energy units. So here's another example of looking at the fact that electrons can only exist in these discrete shells, this specific distance from the nucleus. Those are the only levels that are allowed. So we don't have a slide, we have stair steps. For example, we can have an electron go from, so we have ground level here, which would be n equals 1, 2, 3, 4, 5. So an electron can drop in energy from the 5th to the 4th, and it's not going to give up a very high energy wave, right? It's red, which is on the lower end of the electromagnetic spectrum. Versus if we jump from the 3rd energy level down to the 1st energy level, we see there's a much larger drop, much larger energy, therefore we would see a higher energy wavelength. Red versus green. When we are at n equals 1, our principal quantum number n equals 1, we are at the ground level, and this is the most stable. This is the least energetic, and that is what all chemical species are always trying to get to. All atoms, all elements, electrons, whatever it may be, we want the lowest possible energy. That's the way that reactions shift towards. So electrons can have all kinds of different transitions in a hydrogen atom. It doesn't just have to be in the visible range, but that is the Balmer series, not all of them. But notice that the Balmer series, we're always transitioning to the 2nd level, or 2nd energy level. The Lyman series always transitions to the 1st, Paschen series to the 3rd, Brackett series to the 4th. So these are scientists that studied these different electron transitions and got to name them after themselves. So what are we looking at here? How can we figure out what the energy difference is for a photon? So the I and the F stand for initial and final. We can start off at our initial energy level, whatever that may be. We end at a final energy level, whatever that may be. If we want to find the difference in energy, this delta symbol means that it means the change in, or take the difference of. So we take the difference of the two energy levels, and we come here and we have the Rydberg formula, which then allows us to, say, calculate the energy transition from when an electron starts at n equals 4 and finishes at n equals 2. So all of these energies are demonstrated here with the specific transitions. We cannot have anything transitioning to a 2.5 level or a 3 1/3. That just is not allowed. So we can only transition between these set steps. Electrons exist either here, or but not anywhere in between. So the dual nature of the electron. So we're saying that light can travel both as a wave and a particle. These two things in a way contradict each other. And when you set up an experiment, if you're setting up the experiment to see that light behaves as a wave, that's what you'll find. If you set up an experiment to see that light behaves as a particle, that's what you will find. So how do we know that this electronic energy is quantized? Well, if we look at a guitar, we know that we can pluck a string and it's going to vibrate. And those vibrations are set depending upon where you're holding your finger at along the string. We have one half wavelength, 2 half wavelengths, 3 half wavelengths, etc. We can never end up with a situation if we take this example and move it over here to where electrons are allowed to travel. We can't have anything that's in between, right? This was what I was talking about in the last slide. We cannot have a 3 1/3, okay? The wavelengths are always going to have to constructively interfere with each other, because if they don't, basically that would mean that an electron would be able to just tunnel into the nucleus at any given point, because they'd continue to lose energy and the electrons would continue to get absorbed into the nucleus, changing the element. So de Broglie studied that, yes, he reasoned that an electron is both a particle and a wave, and therefore anything that's traveling with a specific speed can also behave as a wave. So a ping pong ball or a fastball, when a pitcher throws a fastball, there is a wavelength associated with that. We can't see it with the naked eye because the baseball is fairly massive compared to that of an electron. Remember, an electron is I think 10 to the negative 26 kilograms or something like that. It's very, very tiny in mass. Continuing on with quantum mechanics, the Heisenberg uncertainty principle states that at any given moment, you cannot know precisely the location of the electron and its momentum, or the path that it's traveling. So I can't know location and speed, basically, at the same time. I can study one or the other. It's like if you went to a race and they did a photo finish. Whoever finished, or when they took the picture, that was a snapshot of where these things were at this given point in time. However, it doesn't tell you how fast the cars were going. You have to have a radar gun. So if you have a radar gun, you can measure the speed, but the speed has to be measured over, there's a change in distance. So we don't know where the car is if we're just measuring the speed. So it's the same way with an electron. And the uncertainty principle here is demonstrated by saying there is some variance in the position times some variance in the momentum, which momentum is simply mass times velocity. You do not have to worry about solving this equation. So Schrödinger came along and tried to come up with a way to describe mathematically how these electrons travel, where they're allowed to be at. And Schrödinger came up with this wave equation. And within this wave equation, we have these functions which describe or allow us to solve his equation. Now, the best part about this is what happens when we square this wave function. And that tells us where we are most likely to find our electron. So in what space? We'll talk about in a minute what atomic orbital means. But where is this electron allowed to be at? Electron density. So where is it that most of the electrons are located? If you start with one electron, it's most likely to be found closest to the nucleus. That should make sense to us. So his equation with his wave functions, once we square that, gives a really good approximation of where we can find an electron. So we have our nucleus, and we have this green coloring to show, hey, this is where the electron is most likely to be found. And I'll talk to you in a minute about what this 1s thing means as well. So as we start filling electrons, we start closest to the nucleus, and then we have to move farther and farther out. So the more electrons that you have, the more likely you are to find them further away from the nucleus. So here, this tells us, what is your distance from the nucleus when you are a specific electron? Excuse me. So we're going to talk about 4 quantum numbers which allow us to solve that wave equation, to find those wave functions to determine then where our electrons are found. The principal quantum number, n, was discussed when we looked at Bohr's theory of the hydrogen atom. N has allowable values of 1, 2, 3, 4, 5, 6, 7, etc. N is never allowed to be 0. If n was 0, it would mean it was in the nucleus. Electrons aren't allowed to be in the nucleus. So the principal quantum number tells us the distance from the nucleus and or the specific energy level with which that electron is allowed to be at. So distance from the nucleus, energy level, those two things mean the same thing. The number in front of the letter here tells us our principal quantum number. So we get further away from the nucleus as our principal quantum number goes up. The second quantum number is the angular momentum quantum number, little l. And L depends on your values of n. So basically, if n is 1, L can only be 0. So we're always looking at L values that are at least 1 less than your given n values, which is what this means here. Excuse me. So when we have L equals 0, we have the s orbital. When we have L equals 1, we have a p orbital. When we have L equals 2, we have the d orbital. And when we have L equals 3, we have an f orbital. So what this is meaning over here, right? We have n's, which show us our distance from the nucleus, our energy level. So at energy level 1, you're only allowed to have an s orbital. When you get to energy level 2, you start with having an s orbital, and then you're allowed a p orbital as well. Here, we have an s, a p, and a d. So in the 3rd energy level, you allow these different orbitals. At the 4th energy level, you're allowed an s, a p, a d, and an f. So we're looking at, these are just the different places that we can put our electrons. So the angular momentum quantum number describes the shape with which the electron is allowed to be in. So when we look at a density map, is it going to be in a sphere? We can look at other shapes too. So angular momentum says this is the shape of the cloud with which the electron is allowed to be in. So here's what some of our shapes are. Our simplest is our s orbital, which is a sphere. When we have L equals 1, our p orbitals, we have basically a figure 8 or an infinity sign. We have 3 different options here. When we have L equals 2, we have our d orbitals, and we have 5 different options here. Most of them are kind of like a 4-leaf clover, and then you have this strange one with the ring in the middle. Now you don't have to memorize px, py, pz, etc. We'll talk in a minute about what that actually means. Now I would like to point out that no matter what your orbital is, you are only allowed to have 2 electrons per orbital. So 2 electrons, 2 electrons, 2 electrons, doesn't matter the energy level. 2 electrons, 2 electrons, 2 electrons, doesn't matter what shape it is. Down here, right? 2, 2, 2, 2, 2. So in your d orbitals, you're allowed a maximum of 10 electrons. In your p orbitals, you're allowed a maximum of 6. In your s orbitals, you're allowed a maximum of 2 electrons. And f orbitals are really complicated, so we never really look at the shapes, but basically it would be like putting one of these infinity symbols on top of this. So now instead of a 4-leaf clover, it's like we have a 6-leaf clover. And in your f orbitals, you have a total of 7 orbitals, 2 electrons each, which means there's a max of 14. The 3rd quantum number is the magnetic quantum number, m sub L. And m sub L depends on L. So what are we looking at here? Whatever the value of L is, m sub L is allowed to be that, the negative all the way up to the positive. So when we have L equals 1, m sub L is negative 1, 0, or 1. So we count from the negative of our value, of our L value, up to the positive value. If L equals 2, we have the range from negative 2 all the way up to 2. Those are allowable values. And we would continue on. When L equals 3, we're allowed m sub L of negative 3 all the way to positive 3. So our magnetic quantum number describes the orientation in space for which your shape is allowed to be. So we looked at L values, which told us the shape. This is where our electron can exist. In which direction is that shape facing? That's what we're looking at with magnetic quantum number. So spatial orientation. So we can go back and look at what's going on here with now the px, py, pz designation. Here I have allowable m sub L values for my p orbitals of negative 1, 0, or 1, which means that I'm allowed to have it along the x-axis, along the y-axis, or along the z-axis. I have 5 numbers here, negative 2 all the way to positive 2, for my 5 different d orbitals. And those tell us, once again, here we are on the plane, the xy plane. Here we are in the middle, in between our xy plane, right? In the middle of our xz plane, in the middle of our yz plane. So this is what this is telling us. These are the different directions with which my orbital can face. And the last quantum number is the spin quantum number, m sub s. And there's only 2 possible values, and it does not depend on anything else. It's either positive half or negative half. Which basically means that an electron is allowed to spin clockwise or counterclockwise. So how do we discover this? When we have an atom beam going through this slit screen, magnetic field is applied, and we see that the atoms are splitting based on which way their electrons are spinning. So Positive 1/2 would be attracted to one end of the magnet, and the negative 1/2 would be attracted to the other end of the magnet. If this didn't exist, we would just expect to see one beam travel through the middle with the zero charge. Now, the difference here, diamagnetism, paramagnetism. Di means here that you have two electrons paired, meaning you have one that's spinning one way, one that's spinning the other way, therefore they cancel each other out. Paramagnetism is when you have electrons that are facing the same direction. So let's pretend I flip this arrow around. Now I have parallel spinning electrons, two up arrows or two down arrows, and that is what is considered to be paramagnetic. So there are parallel spins, not paired in the way that it is up here in terms of one up, one down. Now, when things are paramagnetic, that is when what we know in layman's terms is as to something being magnetic. So things being magnetic have to do with the direction with which the electrons are spinning, and having those unpaired electrons, meaning I've got parallel spins. So we have those four quantum numbers. It's like an address for an electron. N tells us our energy level, which for you or I would be like, we live in the state of Tennessee. L tells us the shape of the orbital. So what city do you live in? M sub L tells us which direction that shape is allowed to face. What street do you live on? M sub S tells us which way are we spinning. What's your actual house number? There's our address. This tells us going from our broadest location down to very specific. So what do these designations here mean? Shell, subshell, orbital. So your shell is related to your N. Shell is your energy level or your distance away from the nucleus. Within your shell, you can have a set of subshells, which tells us our L value. Is it S orbitals? Are there S and P? Are there S, P, and D orbitals? So those are your subshells. So what is your orbital then? Your orbital is telling you your M sub L value, or what is the direction in space with which your subshell is allowed. Say that 5 times fast. So shell is your energy level, subshell is your shape, and your orbital tells you the direction with which your shape is facing. It's our address. We get specific about where we are finding an electron. So here's a diagram looking energy going from 0 up to a higher value. Doesn't matter what that value is. But what we notice when we have a single electron atom like hydrogen is that when you're in the second energy level, there is no difference between your S and your P orbitals. However, when we get into atoms that have more than one electron, which is every other atom, we start to see that there is a difference. Even though we're in the second energy level, the P orbitals are a little higher in energy than the S. And here we see that trend of the P orbitals continuing to be a little bit higher than the S. Now notice here there's a little difference where we have the 3D orbital is actually lower in energy than the 4P orbital. And I'll show you guys how to use your periodic tables, and you don't have to memorize then what order things go in. But when we start to put in our electrons, we're always going to go from the bottom up to the top, lowest in energy to higher in energy, because lower energy is always stable. So when we do this, we can write out what's called an electron configuration. And this tells us the placement or the location of each of our electrons. Each electron has to have its own 4 set of quantum numbers, which is what the Pauli exclusion principle means. No 2 electrons can have the same 4 numbers. This would mean that those 2 electrons were existing in the exact same space at the exact same time, and that is physically impossible. So you can have 1, 0, 0, 1/2 and 1, 0, 0, negative 1/2. So 3 out of the 4 numbers can be the same. And those numbers I just gave you were for an electron in the s orbital and then putting another electron in the 1s orbital. The Aufbau principle is the building up principle, which states that we are going to fill our electrons in the lowest energy orbitals first and continue to move up the scale. Lower energy to higher energy. Aufbau means building up. And then Hund's rule states that when we have degenerate energy levels, and I'll talk to you about what degenerate means, is that we are going to fill our electrons in a way that we are going to maximize parallel spins. So what is a degenerate orbital? Right here, I have 3 of the same orbitals at the same energy level. So what this means is I'm going to put an electron here, then I would put one here, then I would put one here. And when I place my electrons, they would all be facing the same way. They would all be spin up or they would all be spin down. So this is what is meant by a degenerate energy level. So how do we write an electron configuration? 1s1. That tells me that I'm in the first energy level, my orbital shape is an S, and I have 1 electron there. So this is how we're going to write out electron configurations. We can also represent them using an orbital diagram. Every arrow represents an electron. So for our simplest atom, hydrogen, we have 1s1. Helium, 1s2. Lithium, 1s2, 2s1. So we can never have 1s3 because the s orbital can only hold 2 electrons. So what do we do when we finish filling out 1 orbital? We have to move to the next energy level and start filling out that orbital. Beryllium, 1s2, 2s2. If we add our exponents together, it should give us the total number of electrons that we have. And recall from the periodic table, your atomic number tells you both protons and electrons for a neutral atom. So you would notice that beryllium is atomic number 4. So boron, we keep going, 1s2, 2s2, 2p1. 5 electrons. We filled our s orbitals first and then moved across to the p orbitals. So we continue to do this. We continue to fill our electrons until we run out of space in an orbital. For example, if we get to neon, we would see that this became 2p6. What happens when we hit the end of the row? Well, we just go down 1 more level, increasing by 1, which means then we'd end up in the 3rd energy level, starting at the beginning with S. 3s, continue. So this is a great way to look at our periodic table, that we can just read it from left to right like a book. We don't have to memorize the order of our shells by any means. So we start with the 1s. Keep in mind that hydrogen is the only atom that's going to have an electron configuration where there's an S1, 1s1. Everything else has to be a 1s2. So from helium down, it has to be 1s2. So keep in mind that these are separate, but they're the s orbital, first energy level s orbital. Second row, second energy level. Third row, third energy level. Fourth row, fourth energy level, except for our Ds. Our transition metals do something D for different. So we always have to remember to start with our 3rd energy level here once we run into our transition metals. This is simply because in our 3rd energy level, we are allowed SPD orbitals. However, these elements do not have enough electrons to fill the d orbitals. So we can't put any electrons in there yet, but it's like an empty pocket. Your pockets exist whether you have anything in them or not. Orbitals are like electron pockets. So once again, we're just reading left to right across our periodic table. So it tells us we go 1s to 2s to 2p to 3s to 3p to 4s, 3d, 4p. I hit the end of the row and I just continue to do this, 5s, 4d, 5p, and I'm filling my electrons in those specific orbitals, remembering that maximum of 2 electrons, maximum of 10 electrons, maximum of 6 electrons, maximum of 14 electrons. And if you notice, if you've blocked this off on your own periodic table, group 1, group 2, there's 2 elements next to each other. Here, there's 10. Here, there's 6. And here, there's 14. So you don't even have to remember the number of electrons you put there. You can just count on your periodic table. So this slide here shows what our standard notation is for our outermost electrons, which we call valence electrons, and we'll talk more about that later. So 1 electron, 2 electrons, we move over here, total of 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7 electrons, 8 electrons. Look at that, our trend of, if we're looking at our A groups, our representative elements, 1, 2, 3, 4, 5, 6, 7, 8, hey, it matches our group number, telling us how many valence electrons we should expect to see. Now, the Ds are a little different. We have some interesting elements which don't necessarily follow the rules. I encourage you to look in your book to figure out what those elements are. And continuing on. So we have the last bit of the chapter here is looking at effective nuclear charge, and this will come into play in looking at different periodic trends. So your effective nuclear charge is looking at, so we have our protons, which are positive. We have our electrons, which are negative. So what type of positive attraction is that electron feeling? The effective nuclear charge comes from the fact that some of the electrons are shielded. So we have electrons that are close to the nucleus, which are shielding that positivity away from the electrons and the outer orbitals. So what is the effective charge? What is the Z here, right? That's atomic number, 3 protons in lithium. However, an outer electron is only going to feel as if there's 1.28 protons. Now, we know there can't be any half protons, but it's looking at this diminishing positive charge that results from these inner orbital electrons shielding our outer orbital electrons. You do not have to memorize these numbers. There is a calculation to figure out what your effective charge is based on how many electrons are in s orbitals and p orbitals, etc. But what we really just want to think about is when we're looking at these trends, and we'll study the first trend here in a second, is that how tightly are the electrons being pulled towards the nucleus? And that will help us to determine different things like size, ionization energy, electron affinity, etc. So first periodic trend to look at is atomic radii. And there's different ways that we can measure atomic radii. In a metallic solid, you can measure, because the atoms are lined up very specifically in crystalline structure. In a covalent molecule where we have non-metals bonded to each other, we have to have a different way in which we measure them, because here we have our orbitals are actually overlapping, where in metallic bonding, the electrons are allowed to just travel through because of the energy levels. So what's our trend? We will notice that as we go across the periodic table, so moving from left to right, our atoms get smaller. And this is because our effective nuclear charge increases as we go from left to right. Why is this? Well, here we're in the second energy level. So when the electrons are getting added, they're getting added into that same distance. Now, every time we add an electron, we're also adding a proton. Protons are bigger in size, so they're able to pull in those electrons closer. Our effective nuclear charge is going up as we go across the table. Now, as we go down a group, we notice that the atoms are getting bigger. Why is this? Well, once we've hit the end of the row, we know we can't put any more electrons there, which means then we have to start another energy level out. So we increase our size, basically, 1, because we're adding more electrons, and 2, because those electrons feel a much less effective nuclear charge than what those inner electrons do. So anytime you're adding more electrons into a new energy level, this is a new energy level, we're getting bigger. Even though we're adding electrons here, we're staying in the same energy level, so we get smaller. So our biggest element is going to be found at the left-hand, the bottom left-hand corner of our periodic table, and our smallest element is going to be found in the upper right-hand corner of our periodic table. So effective nuclear charge gets bigger this way, effective nuclear charge gets bigger this way. And another way to just look at our trends in atomic radii, if we notice here, lithium, sodium, potassium, rubidium, cesium, we are going down the alkali metal group, noticing that our atomic size increases. Now, If we look at lithium through fluorine, here we are going across a row, and we can see the trend that, yes, fluorine is smaller in size than lithium. This has to do with effective nuclear charges. So in class, we're going to practice using the speed of light equation, Planck's equation, the Rydberg equation, setting up quantum numbers, and looking at these different trends. Study, study.